Okay, let's just jump right into this explainer and uncover the hidden quantum mechanics powering the very device you're watching this on right now. You might see a sleek screen and a nice metal casing, but underneath all of that, there is an entire universe of quantum physics working in absolute perfect harmony just to bring you this image.
I mean, we really have to ask ourselves, how on earth does a lifeless, completely inert crystal of silicone learn to think? To answer that, we have to totally shift our perspective. We need to shrink all the way down to the quantum realm and look at how electricity actually flows. It's not just some continuous, predictable stream of water in a pipe. We're talking particle by individual particle, governed by rules that completely defy our everyday intuition.
So, think of this explainer as our system boot sequence. We're going to cover 1, the quantum gridlock, 2, energy bands and gaps, 3, the metallic highway, 4, semiconductors and doping, 5, the magic p-n junction, and finally 6, transistors and modern tech. We'll start at the atomic level and scale all the way up to the microchips driving modern technology. All right, part 1, the quantum gridlock. So imagine an isolated, totally neutral copper atom. It stacks its 29 electrons beautifully into discrete, separate subshells. Very orderly, right? But watch what happens when things get crowded. When you bring billions of these atoms together and pack them into a 3D crystal lattice, those individual subshells start overlapping. And that's when the Pauli exclusion principle kicks in. This principle strictly prevents electrons from sharing the exact same quantum state, which effectively forces these atomic levels to merge into something entirely new. Which brings us to part 2. Energy bands and gaps. As those overlapping atomic levels merge, they form these massive, closely spaced bands of allowed energy. But, and this is absolutely crucial, between them are ranges of energy that no electron is allowed to possess. Think of the energy bands as open highway lanes, where electrons are free to travel, and the energy gaps as these massive, impenetrable concrete medians, where electrons are strictly forbidden from ever existing. This fundamental layout dictates literally everything about a material. Take insulators, like diamond, for example. They have completely filled bands with massive energy gaps right above them. In diamond, that gap is a whopping 5.5 electron volts. The electrons are stuck in a total quantum gridlock. They simply don't have the thermal energy to jump that massive gap. Metals, on the other hand, they have partially filled bands, so they have plenty of open lanes right above their highest electrons, allowing for super easy movement and conductivity. Let's dive deeper into that open lane in part 3, the metallic highway. To really understand this free-flowing highway, we have to look at Fermi energy. See, even if we freeze a block of copper all the way down to absolute zero, the motion inside doesn't just stop. The Pauli exclusion principle forces those conduction electrons to stack up in the available energy levels, one by one, up to a maximum height. We call that the Fermi energy. For copper, that's 7.0 electron volts. It's kind of like cars backing up at a red light. They can't occupy the exact same physical space, so they just keep stacking backward down the highway. Now, to truly map this highway and understand conductivity at any temperature, we have to calculate 2 vital things. First, the density of states. Think of this as counting the available seats, or energy levels per given volume. Then, we use something called Fermi-Dirac statistics to figure out the occupancy probability. Basically, what are the exact odds that an electron is actually sitting in one of those seats? By combining the available seats with the probability of them being filled, we know exactly how our quantum traffic is distributed. And because of this quantum stacking up to the Fermi level, the highest energy electrons in copper aren't just chilling there. Even at absolute zero, they are zipping around at a staggering Fermi speed of 1.6 million meters per second. No way, right? But it's true. Okay, moving on to part 4, semiconductors and doping. So comparing our super fast copper highway with pure silicon reveals a pretty stark contrast. Copper has astronomically more charge carriers than pure silicon. But silicon has a secret weapon. Its energy gap is only 1.1 electron volts. That is a small enough gap that we can actually manipulate the material. We can use thermal energy or add impurities to boost electrons right across that tiny gap and into the conduction band. And by intentionally adding those impurities, a really clever process called doping, we take the wheel. If we dope silicon with generous phosphorus atoms, which have 5 valence electrons, they act as donors. We end up with an N-type material loaded with extra free-flowing negative majority carriers in the conduction band. On the flip side, by adding aluminum, which is an acceptor with only 3 valence electrons, we create positive empty spaces called holes in the valence band. This is a P-type material. and those holes actually flow through the lattice just like positive charges. Now we reach the absolute climax of this explainer. Part 5. The magic PN junction. When you jam an N-type and a P-type semiconductor together at a single junction plane, this incredible instantaneous sequence kicks off. Immediately, a diffusion current flows as electrons rush across to fill the holes on the P side. But this sudden movement leaves behind fixed charged ions, which builds up a space charge. This instantly creates a depletion zone right at the border, a barrier with its own built-in contact potential that literally blocks any further traffic. And here is where the real magic happens. By applying an external voltage, we can manipulate that exact barrier. If we use a forward bias, we shrink the depletion zone, completely opening the floodgates for massive current flow. But if we apply a back bias, we widen that depletion zone, slamming the traffic shut entirely. With just a tiny shift in voltage, we have absolute total control over the electricity. Which leads us to our final section, Part 6, Transistors and Modern Tech. This simple PN junction barrier, it is the fundamental building block for almost every piece of digital technology you use on a daily basis. We're talking junction rectifiers that convert alternating current to direct current, light-emitting diodes, junction lasers that read optical discs, and, of course, the almighty transistor. Let's look at a really fun example. In a specific semiconductor material, like gallium arsenide phosphide, when we forward bias the junction and force an electron across the gap to fall into a hole, it sheds its exact energy gap of 1.9 electron volts as a 650 nanometer photon. And we see this with our own eyes as brilliant red light. We are literally lighting up our world through LEDs and lasers by carefully managing these quantum reaps. But we can take it even a step further with the MOSFET. That's the metal oxide semiconductor field effect transistor. By chaining these concepts together into a 3-terminal device, we can use an electric field at the gate to control the flow of electrons between the source and the drain. Basically, we've created microscopic switches that can amplify signals and perform the billions of logic operations a second required inside your computer chip. So what you should really take away from all this is that the entire digital age, including the immense processing power of the smartphone right in your pocket, is completely reliant on the careful manipulation of invisible microscopic quantum gridlock. We've taken the strange, counterintuitive rules of energy bands and quantum mechanics, and we've turned them into the very bedrock of our modern society. Which brings us to a final thought. It really makes you wonder, doesn't it? If we can build a synthetic brain from lifeless silicon just by controlling microscopic energy gaps, what quantum leap is waiting for us next? As we continue to shrink these components down to the literal atomic level, what new quantum barriers will we learn to cross next? Keep that in mind next time you're effortlessly scrolling on your device. Thanks for watching this explainer, and we'll catch you in the next one.